Okay, so what we want to do in this case is we want to prove that 4 over 3 pi r cubed is the volume of a sphere, right? Now, how are we going to do that? We're going to do it using some Calc 4, right? Or using some Calc 3, whatever college you go to, I don't really care. But we know that the volume is equal to the triple integral dv, right? That's the volume. Okay, now, obviously we're some region E. Now let's first start by defining the region E. Now keep in mind, it's 4 over 3 pi r cubed. There's no, this is just like a perfect sphere, right? We don't have to worry about this sphere being a little rounded somewhere else and pulled in a different direction. So it's a perfect sphere, okay? Perfect sphere with a radius r. So we can just literally write E is equal to perfect sphere. Perfect sphere with equal radiuses. And obviously every sphere, but I just have to say that, right? Equal radius centered at the origin. Radius r, right? So that's the radius, okay. So what does it mean? Well, we know that if we're to draw these axes, z, x, y, right, our sphere is right here, right? This is what we got. That's our sphere. Okay, now we know that our sphere, if we want to describe how round it is, or how circular it is, we could use the variable theta. And we would see that theta is bounded from 0 to 2 pi, so it fully goes around, right? Now, if we wanted to see the same thing but from top to bottom, does it go round from top to bottom? We use phi. So phi is from 0 to pi, right? So remember, phi is like the windshield wiper going down, and then theta is going around like this, right? Phi goes up and down, theta goes around. And then r, well, radius itself, right? We'll just write radius r is equal to 0 to r. And I'm gonna use a big capital R here and here, just so for the sake of notation, so it looks a little bit better. Okay, so these are our parameters, and let's go about this. Now, note that we have dv here. Is dv really going to be helpful in this case? Or would we want to use a Jacobian, right? A change, right? So what do we know? These are our bounds. But if you just put the stuff straight in, you're not going to get the answer. You won't even be able to integrate really because we have dv here, which would be dx, dy, dz. So dv, we go yellow here, dv is equal to dx, dy, dz. But we have a sphere, so we want to use spherical coordinates, right? Spherical coordinates would be, so we could have, we'll call it d, r for radius, for phi, d theta, d phi, and then we have r squared sine phi, right? This is right here. Jacobian, spherical Jacobian. So I hope everybody understands that part right here. And I can write it, I'll write it a little bit nicer. I mean, it's fine this way. The order of the differentials is a little skewed. It's completely fine to write it like that. But you'll see in a second what I mean and how this is going to help us get our answer. So now, when we write our integral, so it'll be 0 to 2 pi, 0 to pi, and then 0 to big R. And then dv, we're going to replace it with this stuff. So let's go with, now, note we have the r squared here. So r squared sine phi. And then now, right, dr. Actually, one second. I should write, I'm just trying to keep the notation proper here. little r, little r, and little r. So there we go. 100% correct notation. No need to worry. Then we got d phi and d theta. Okay, so here we go. Right? That's what we have. Now we see that this integral has multiples in it. So what that means is that we can say that this integral is equivalent equal to 2 pi 0 d theta multiplied by what? Pi to 0 sine phi d phi multiplied by r to 0 r squared dr. Right? This is completely true. We can do this, right? That's the really nice thing about triple integrals if they have multiples. I mean, if there's no like plus or minus in the middle of the integrand, is that you can just do this. So that's going to become 2 pi. The other one's going to be sine phi, which would be what? Negative, factor it out, negative cosine pi minus cosine 0 plus, multiplied by r squared dr. That's going to become r cubed over 3. Right, so there we go. We see that there. And then cosine pi is what? That's 1, cosine 0. That's negative 1. Negative 1 minus 1 is negative 2. Negative 2 times what? What is that? That's a negative. So we get 2 pi times, again, this is negative 1. This is 1, and a negative 1 out here. So negative 1 minus 1 is negative 2. Negative 2 times negative 1 is 2. So 2 pi times 2 times r cubed over 3. What is that bad boy going to be? 2 pi times 2 is 4 pi. 4 pi over 3 r cubed. Oh my god, I can't write the r cubed. There we go. Look at that. See? That is the equation of a sphere. Makes sense, right? The Jacobian part here, you should just know your Jacobians, and we can show you, if you don't know your Jacobians, I have videos on my channel about Jacobians, right? But generally, you should always memorize your spherical Jacobian. And in fact, I'll write it out here, right? Your spherical Jacobian, I'm just going to say SPJ. You always have it as r squared sine phi d phi, or you get, the order of the differentials can always change depending on how you set up the integral, right? D theta. Right? That's your spherical Jacobian, and it makes things really nice, really fast, and really simple to do. And then you could find anything like spherical, usually with your spherical Jacobian, a lot quicker than using other coordinate system. Okay, I hope that made sense, and hope you guys will do good in your Calc 4.